Welcome back to ECE 542, 442. I have to remember what class I'm in. I've had office hours dealing with other topics today, so I'm a little bit disconnected from 442, 542, but I think I will capture your attention when I start going through the process for exam number 1, and I don't know if you can see what's in red for exam number 1. If you can't see it there, you probably see it there. But today what we are talking about is material that will be on exam number 2, but I think hearing it and understanding it will benefit you for exam number 1. Meaning we'll talk about region of convergence. We'll actually start today with a quiz, but before we do that, I want to give you the process for exam number 1 if you haven't figured that out by looking at some of the old practice exams. And in fact, this exam will be a little bit different because come Wednesday, we'll have 4 times this number of people in the room. And for that reason, I want to be able to grade the exams before December, and the exam will actually be multiple choice. The structure will be different a little bit, but you will then have more opportunities to demonstrate your understanding and knowledge of the material. There'll be more than just 4 questions. There will be 20 questions on the exam, and they will be little pieces or parts of maybe a larger problem. But if you understand what is on exam number or on the practice exams, and if you can work those problems, you should be able to work the problems that will be on the exam number 1 on Wednesday. Homework number 3, which is dealing with the material that we're talking about today, is due, already in March, the 2nd of March. But today, as I had promised, we're going to talk about the process for exam 1. We'll do a quiz. It's a thumbs up, thumbs down, or a thumbs horizontal for your answer. We'll try to make this 3 possible answers. And then we'll go through the importance of the region of convergence with examples, which is really picking up from where we left off at the last lecture. And then we'll talk about 3 possible region of convergence patterns if we have 2 poles, and inverse Z transforms after that. Since it's multiple choice, you'll need to bubble or indicate your answer on the answer sheet. But I want you to show your work on the physical paper that I will give you that contains the exam. If there's questions or issues, or I want to see, do you really know what's going on with the material, that will be demonstrated by your work on the hard copy paper. You can bring 1 sheet of notes. Yes? So if you guess and get it right, do you get full credit? You might try to show some work, but that will be up to me to decide. I can actually channel all 90 some of you, so I understand exactly where you are in terms of your understanding. And those that are online, I'm actually starting to be able to make connection with you as well. If you're watching this, you can see that I rolled my eyes all the way back into my head and on that comment. Yes? There probably will not be any partial credit. The question was, will there be any partial credit? I think this exam, I have written it to where there's 1 answer, or what I think there to be 1 answer. If I made a mistake, there's always that 5th choice, which is none of the above. And I could have made a mistake. Yes?
So then what's the point of us showing our work if there's no
If. What's the point of you showing your work? Well, I hope you show your work so that you can figure out what the problem is trying to ask you for. So you have to do some work, I hope, rather than just circle a bubble. You better write down some information in order to derive your particular answer. It's really more for you, but if there's an issue, oh, I forgot to bubble that one. Maybe we can go back and look at your work and see what actually you did do. Oh, you were guessing the whole exam and you just forgot to guess on that one. Well, then maybe, let's see, I need to channel, then that one will be 0. Okay? So it is a change, but you can bring the one sheet of notes front and back in addition to the Z-transform table that's on D2L. So you will have 2 pieces of paper. One will just have one side of information on it, which is the Z-transform table. The other one can have up to front and back information on it. And a calculator and something to write with. Not allowed, no neighbor, no computer, no cell phone, no textbooks. You'll put those to the side in your backpack, on silent, etc. Other questions on exam number 1? Here's the quiz. Here's the picture, and I've shaded the region of convergence. And the question is, for what values of n is x of n defined? Where capital X of z has a pole located at z equal to a. I want you now to determine, based on this picture of the pole and the region of convergence, I need you to tell me what values of n is little x of n defined for. And you have 3 choices. You could say, oh, n is when the values of n that are non-negative. That would be a thumbs up. A thumbs down would be the opposite, when n is negative. Two-sided, you're going to have the horizontal thumb or a level thumb. Those are the 3 choices. Do you need to look at this any longer? Can you now determine what you would respond to that question? And I'm going to count to 3, and at the end of 3, you show me your thumb. So that this way people can't look around and say, oh, everybody looks like their thumb is this direction. That's how I'm going to answer.
You show the up is
Causal is thumbs up. Thumbs down is non-causal. And two-sided is thumb level. Ready? 1, 2, 3. So it looks like everybody's getting that. That's the correct answer for question number 1. Let's do question number 2. Is x of n, question? You just guessed? Well, then I'm going to count that one wrong on the exam because I can channel. Okay? So why is this one causal? How do you rationalize that answer rather than just guess? What I would maybe do is I would say, oh, this is now giving me x, capital X of z is this infinite sum of x of n z to the minus n. Well, I would just start writing if I had a little bit more space, and you'll want to on your exam. This is why you want to write on your exam. You would say, oh, dot, 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 x plus x of minus 1, z to the minus minus 1, which ends up plus 1, plus x of 0, z to the minus 1, plus x of 1, to the minus 0, z to the minus 1, and so on. Then I would say, okay, let me look at an extreme value of z that belongs to this region of convergence, that's in this shaded region. And I would say, well, here's a point, and in fact, that point could go all the way off to infinity. And then I would, so that's kind of out there in the cloud. That's going way out there to z going to infinity. And I would put that value of z into this infinite sum, this series. And I would say, are there particular coefficients that have to be 0 if this series actually gives me a bounded numerical answer for all z's that are in the blue region or that are in the region of convergence? The region of convergence is unbounded, is it not? It's unbounded, meaning z goes unbounded all the way to infinity. If I plug z going off to infinity into this term right here, what would happen? If I set z equal, and this is supposed to be a plus sign, if now you have to make sure we're all seeing this properly. Now I plug, that's z to the 1, and I have z squared to the left, I have z cubed to the left. I plug in a z value there that's going off to infinity, and what does that do to my sum? My sum goes unbounded. That forces all of these coefficients, these sequence values, to be equal to 0. It forces that one, and it forces all of those there to the left to have coefficients or weights that are scaling these positive powers of z. X of minus 1 gets scaled by z. X of minus 2 gets scaled by z squared. All of those have to be bounded, which says, oh, their coefficients, the weightings, must be 0. They have to be 0. If that's the case, then what are the values of little n that are non-zero? Those are the ones that are on the right side, and those are the ones that correspond to the causal sequence. That's maybe more explanation that I wanted to provide for the quiz. Now you better be able to ace everything. Okay, question?
So is one way to look at it is to have your poles at least to be inside of the ROC?
So now the question was, is one way to look at it that your poles are inside the ROC? That's one way to think about your time sequence being causal. That all of your poles are interior to the region of convergence. That's one way of thinking about, oh, that leads to a causal sequence. Did that help explain your guess? Or now, whoa, I'm giving you the exam here, whoa. I'll have to edit that out. Yeah, just put it on super slow motion. That's the way you listen to it anyway. Ha ha. All right. Question 2. Are we ready for question 2? Is this sequence, A is the value of that pole raised to the n, is that bounded? And now we know from question 1 what the values of n are equal to, do we not? I'm giving you way too many clues. Thumbs up, it's bounded. I'm asleep at the wheel. Thumbs down is unbounded. 1, 2, 3. I see a mixture. And a mixture is okay because it depends. It depends on what A is equal to. I didn't define what A was equal to. I didn't say where the unit circle was. So here is x of n equal to a to the n bounded. You could say it depends. There was no middle thumb on this one. So if little a was less in magnitude than 1, then it would be bounded. If a, the magnitude, was bigger than 1, with this region of convergence outside of that pole, we know that it's true for little n positive or non-negative, then if a had a magnitude bigger than 1, that would go unbounded as a sequence of numbers. So that question was, it depends, the answer to that. It could be up or it could be down. You could say, you know what, it's bounded, and then you would have to say on your piece of paper, not just a guess, you would say the magnitude of A is less than 1. Right? Question 3. For what values of n is x of n non-zero? And you have 3 choices. Causal is still thumbs up, non-causal is thumbs down, and two-sided is thumb level. We ready to answer? Or are we ready to guess? 1, 2, 3. So this one, based on the analysis or the explanation that we just went over for question 1, this one you can do exactly the same analysis and convince yourself, hopefully, that it is non-causal. If you did the expansion again, and what point would you you might want to pick an extreme point or location in the region of convergence. Here you might say, oh, well, an extreme value might actually be right there when z is equal to 0. And what happens when z is equal to 0 to that piece? Now we're dividing by 0, which says if x of 1 was anything non-zero, that would make the whole sum blow up, and we can't have that if we have a bounded or a converging series, or this sum of terms is summing to something less than infinity. That now forces this coefficient to equal 0, as well as all of those extra terms that are in the ellipses, in the dot, dot, dot. All of these have coefficients equal to 0. That means all of your sequence values that have a positive argument or a positive time index are going to be 0. Or now you have a non-causal sequence or those are the values of n that allow x of n to be non-zero. If a is bigger than 1, this is question 4, is little x of n, the sequence associated with this picture, bounded? A is bigger than 1, the magnitude of A. And we have this picture. And again, I'm just going to allow you two possible choices, up or down. Thumbs up if it's bounded, thumbs down if it's unbounded. A is bigger than 1, and we have this picture. We ready for our answer? Again, bounded is thumbs up, unbounded is thumbs down. A is bigger than 1. 1, 2, 3. A is bigger than 1, but what's happening? What values of n is this valid? We just answered it in question 3. Negative. So now we have, let's say, 3 to the minus 1. Here I'm just picking a hypothetical. A is now 3. But this is like 1/3 to the 1. 1/3 squared. 1/3 cubed. That's collapsing. So in fact, this should have been a thumbs up. You needed A to be bigger than 1 if you wanted to have a bounded time sequence for this particular region of convergence picture relative to that pole location. Because now we are looking at A to the n with n less than 0. Or we're now looking at, well, I just picked 3 before. We have 3 to the minus 1 for n less than 0. Or this is now 3 to the n. And you could say, well, that's kind of confusing, but you could relabel that and say, why don't I say L and N are opposites, so this is now what I have. And now I have 1/3 to the L, and L is going positive. Questions on the quiz? Was that for a grade? I didn't see any work. Do you get pity points? That would be great, huh? Well, let's see how I'm feeling. You have to have feelings in order to have pity points, right? Let's see how that works on Wednesday. Come ready to perform. Let's look at now the importance of the region of convergence. Why are we talking about the region of convergence? We need the region of convergence so that we can actually invert from a transform expression. If somebody just hands us a transform expression, we can't really tell you what's happening in the time domain with the corresponding sequence without some additional information, where that additional information is the region of convergence. So we're going to examine 2 different cases with R, or the pole, or the magnitude of this sequence being equal to 1/2 in both cases. We already looked at this one, case 1. This was previous. We derived x1 of z was equal to minus z over z minus 1/2 when x sub 1 of n was 1/2 to the n when n was negative. What did that impose on our region of convergence? Do you remember? So you could start putting this all together if you wanted to, if you needed to. You could say, well, capital X1 of z was this sum from n equal minus 1 to minus infinity. When it's negative, when n is negative, and that was now 1/2 to the n z to the minus n. Or you could now say this is this sum from n equal minus 1 to minus infinity of 1/2 z to the minus 1 to the n. But what do we need to have happen in this case when n is negative? What do we need that common ratio, how do we need that common ratio to behave relative to some particular value that's sort of our sweet spot? The power we're raising this to is always negative. So we're putting whatever is in parentheses in the basement of something. So now what do we need that argument to be if n is negative? Don't we need this common ratio, this 1/2 z to the minus 1? Don't we need it bigger than 1? So that this now tells us that we have 1 over 2z bigger than 1. Or this now says that we have 1/2, if we solve for the magnitude of z, if we multiply both sides by the magnitude of z, we see that this is now our region of convergence. Z, the magnitude of z, needs to lie inside a radius of 1/2. Or here, if we hadn't done this background analysis, we would have been saying, oh, z needs to have a magnitude less than 1/2. That's our region of convergence for this case, case number 1. And that's what we looked at last time. Case 2. This is now for the opposite values of n, or the side opposite to the origin, n equals 0. This is for n greater than or equal to 0. We now have x sub 2 to the n equaling 1/2 to the n when n is greater than or equal to 0. We could derive this again by doing our infinite sum. And what do we know about our common ratio in this case? In order for that sum to give us, or that series, this sum of all of these terms, we want that series to be bounded. What do we know has to be what has to be true for that common ratio? Now n is positive or non-negative. We now know that 1/2 z to the minus 1 needs to be less than 1. Or we now have 1 over 2z less than 1. We multiply by magnitude of z on both sides, and I hope now you see that our region of convergence for case number 2, that would end up with this z transform, capital X sub 2 of z, equaling z over z minus 1/2, with the region of convergence being outside all values of z beyond this value of z equaling 1/2. Let's go through a few more details. We've already kind of done this, but let's do it again. What's another way that I could write x sub 1 of n? I could write it with a switch, where our switch is the unit step function. we could write this as x sub 1 of n is equal to 1/2 to the n. What's in my argument? N. I want that switch to be on as long as little n is negative. So now I need this to be, and I want it to be strictly less than 0. So I don't want to just put minus in because then it would turn on at 0, correct? I need this to be -1, and now when little n is -1, the argument of u of -n-1 is 0, and that's when it turns on. When n is -2, it's now 2 minus 1, or 1. That's positive, the argument. So u is on still. And as long as n just keeps marching in the negative indexed direction, that switch is on. Are we comfortable with either of those two ways of describing this sequence x sub 1 of n? This is now the unit step. And we're using it as a switch. You now should be able to derive this z transform by our comparison of these sums of terms and then scaling one of those by the common ratio and then taking their difference, and then solving for capital X sub 1 of z. What happens to our time domain response, x sub 1 of n in this case, when capital R, here is our R, that's now 1/2, and we're raising it to -1, 1/2 to the -2, 1/2 to the -3. What's the time domain response? Is it bounded or unbounded? This is now unbounded. And in fact, if x sub 1 of n corresponded to an impulse or a pulse response of a system, we would say that that system was unstable. But here let's just talk about that sequence x sub 1 of n. What can you tell me if I now drew this particular sequence and its pole zero diagram relative to the region of convergence? How would I draw the region of convergence here? What would it look like? Or where are my poles and zeros? Here's the z-plane. Hopefully you see that I have a 0 right at the origin. Z equal to 0 will cause that to vanish. And when does the denominator vanish? It vanishes when z is equal to 1/2. I have a pole at 1/2. Where's my region of convergence? Well, this is my region of convergence. And that now is my region of convergence. How does that compare to the unit circle? Here's my unit circle. Here's 1, here's -1, here's j, and here's -j. Can we make a statement about the region of convergence and whether or not the unit circle, which is what this is, does the unit circle lie on top of the region of convergence? Does the region of convergence contain the unit circle? We could say this many different ways. The way I'm going to word it now is I'm going to say the unit circle doesn't lie on the region of convergence. Is that clear? The green dashed circle is not on top of the blue ROC on the rock. Here's our rock right there. There's the region of convergence. It has a disk of size 1/2, of radius 1/2. That's interior to the region of convergence. The region, I'm sorry, to the unit circle. The unit circle does not lie on top of the region of convergence. And that's actually the connection or the disconnect that we can make. Oh, our unit circle is not contained or lying on the region of convergence. Things are unbounded. Doesn't really matter what little n is. We can make that conclusion. Then we can determine what is little n. When is the sequence non-zero? And what else can we say? The ROC, the region of convergence, is interior to all poles. The poles can't lie on the region of convergence. We know that. So the region of convergence is interior to all poles. Then this sequence in the time domain, x1 of n, is an anti-causal time sequence. And that's just the opposite of what somebody stated before when we had all of our poles interior to the region of convergence. Now all of our poles are exterior to the region of convergence. And we know that x1 of n is equal to 0 for all n non-negative. That's anti-causal. The only time x sub 1 of n has a non-zero value is when the argument of its function is negative. When it's positive or non-negative, it's 0. And that's determined by this region of convergence, because we could pick a particular extreme value, and the extreme value in this case would be z equals 0. And then look at our expansion. That's case 1. Case 1 was this picture, and that corresponds to these three comments. And we can say something about the bounded nature of that time sequence because of the relationship between the region of convergence and the unit circle. Here the unit circle is not on top of the region of convergence. Case 2. Here I've already written it both ways. Here it's easier to think of as far as the unit step with this switch. This is still the unit step. We're looking for that switch to be on when its argument is non-negative, and that's true for non-negative values of n. Then we have 1/2 to the n, where n is 0, 1, 2, etc. What does that sequence look like now if we simply sketched it? And sometimes it's helpful to just quickly sketch so that you have time and your mind just starts connecting the dots. What is my value of x sub 2 of n at n equal to 1? That's 1/2. So now we're 1/2 of where we started. At 2, we're 1/2 of that, which is 1/4. At 3, we're 1/2 of that. And you get the picture. Now, just from that picture, you can immediately start answering some of the questions that you might want to answer. But let's now derive this z transform for little x sub 2 of n. We know it's this infinite sum. That's the definition. This is the definition of the z transform. We know, though, that it's only valid for little n that are non-negative. We can throw out the left tail, the negative values for n, and we can now rewrite this and say, oh, this is 1/2 z to the minus 1 to the n. And when is that series going to converge? N is now positive or non-negative. You now have something that you just raised to higher and higher powers, and it's well behaved and it's collapsing, as we saw in this sketch. The common ratio in this case is 1/2 z to the minus 1. That needs to be less than 1. We put the z downstairs, then scale both sides or multiply both sides by the magnitude of z, and we see then that the region of convergence, or the values of z that allow this infinite sum to converge, are values of z beyond this disk of size 1/2. Or x sub 2 of z is now 1 over 1 minus 1/2 z to the minus 1 if we did our comparing of these infinite sums and multiplying the bottom one by this common ratio and then comparing, dividing by that. We could rewrite this as positive powers of z by multiplying by 1, which is z over z, and we now have z over z minus 1/2, and this is true for a region of convergence that's outside of 1/2. How do we put all of that together in this picture? Where are my poles and zeros? They're exactly the same as in case 1, aren't they? I have 1 at the origin, that's the 0, and I have a pole at 1/2. Now how do I shade this? That's determined by this. That's my region of convergence. I now say all z's that are outside that disk of 1/2. Now my region of convergence looks like that. What observations can we make now? Again, this is case number 2. This is when x sub 2 of n was r, where r was 1/2 to the n greater than or equal to 0, or 1/2 to the n u of n. What's the time domain sequence look like? Which we are calling x sub 2 of n, is, that one's bounded. We saw that just by the quick sketch at the very beginning. What do we know about the unit circle and its relationship to the region of convergence? Do you see now that here's our region of convergence, and where is that unit circle relative to the region of convergence? Is it lying on top of the region of convergence, or it's contained in the region of convergence? The unit circle now lies on the region of convergence, and that's the connection This connection is the same, it's just giving us the opposite result as before in case 1. Now we have a well-behaved time sequence when the unit circle lies on top of or lies on the region of convergence. What can we say about the region of convergence in terms of its nature? The region of convergence is exterior to all poles. Why is that? Because we know poles cannot lie on the region of convergence, right? What else can we say? You could now pick any point in that shaded region, and in fact, you can pick a special one and let it zip off to infinity, which means what do we know about the region of convergence? As an area, how extensive is that area? Is it bounded or unbounded? The region of convergence. It's unbounded. That is independent of what the sequence in the time domain is, because we found it was bounded. Why was the time sequence bounded? Because it was a pole of 1/2, which for positive values of n is collapsing. Here then our third point, or our third bullet, is the region of convergence is in fact unbounded and is exterior to all poles. This unbounded has a different sort of interpretation than the bounded and unbounded nature of our sequence in the time domain. Unbounded here means that our area goes off to infinity. We know because of that, though, that we can say something about the causal or anti-causal behavior of x sub 2. X sub 2 is what? A blank sequence, where the blank is causal or anti-causal. It's causal because it's defined for values of n that are non-negative. Or we could now say that x sub 2 of n is equal to 0 for n less than 0. And we know we've computed what this z transform looks like for the sequence little x sub 2 of n. This was z over z minus 1/2 in our region of convergence was such that the magnitude of z is bigger than 1/2. Take-home message. After case 1 and case 2, here's our take-home message. What capital X of z equaling z over z minus 1/2 corresponds to in the time domain, little x of n, depends on the region of convergence. You could have that exact same transform and interpret it two different ways without somebody telling you the region of convergence. You could say, oh, well, that's corresponding to these unbounded sequences with n negative. No, it's x of n, or 1/2 to the n where n is positive or non-negative, and that's when n is positive. It's causal. That's our take-home message. What this transform corresponds to in the time domain, you have to have the region of convergence, or you can't determine what your time domain sequence looks like just from the transform itself. Yes?
So previously you had a negative in Z?
Yes. So now, before, in deriving these, the comment was one of those you had a negative sign. But do you see that I could actually put my negative sign on the time sequence? In this case, this could have given rise to little x of n equaling minus 1/2 to the n for n negative. And that would still be okay. That would be a valid response, but what it's going to be in the time domain here, if we know our region of convergence is outside the pole, then we know what x of 2 of n equals. If we know we have this region of convergence for case 1, now we have a negative sign in between our time domain sequence, 1/2 to the n, and our z transform. So if you actually started with your z transform being z over z minus 1/2, you would have to put that negative sign on the time domain side of the expression if your region of convergence is this disk of size 1/2. So you could always start with the same transform expression, z over z minus 1/2, and give rise to two different time domain sequences. Is that clear? All right, fact. The region of convergence, and now I know that you enjoyed the quiz so much. Let me give you another one. Let me say always, sometimes, and never. The region of convergence, one of these three choices. So let's just say always is up with your thumb, never is down with your thumb, and sometime is horizontal. The region of convergence, blank, contains any poles. And I need you to tell me with your thumb which one you are voting for at the count of 3. 1, 2, 3. So now this one should be never. We said the region of convergence never contains any poles. Did we say anything about the zeros? No. But the poles cannot belong on or in the region of convergence. Let's now look at 3 different possibilities for a region of convergence when we have 2 poles. Suppose now we look at possibility number 1. And now I've already sort of shaded the interior dimension of my region of convergence, let me say here that the region of convergence is going to extend outward from a central void. The central void has a radius of 3/4. There's possibility number one. I have two poles, and in all three of these cases, they're always going to be at 1/2 and 3/4. And I'm now going to draw three different possible region of convergences for those two poles. Here's the first one. Possibility number one. What can you tell me about this scenario? Christian's going to tell me that the region of convergence is where? The region of convergence is outside all the poles, isn't it? And from that, so here ROC is outside all poles. And we can also put this point, and we can, since we shaded those lines, if you couldn't see, are going off to infinity, we can put a hypothetical z value going off to infinity. What's the structure of little x of n? And this might be on the exam. Exam number 1. Could be on exam number 2. It could be on the final. It could be on exam number 3. This you have to know, right? The structure is some coefficient times the mode 1/2 to the n plus some other coefficient alpha 2 times the mode 3/4. Those modes are determined by the poles to the n. But what do we know about what values of n this is valid for based on this structure or this possible region of convergence picture? Because this guy is going off to infinity, we know that all of those negative indices coefficients have to be 0, don't we? We now know we have a causal sequence. We can now say that this is true for n greater than or equal to 0. You can go home now and say, man, I really exercised today. I was doing this all class with my thumb up, down, sideways. Right? You can make it a little bit more animated if you want. I think I just pulled a muscle. Where are we? Oh, x sub a of n. So now I'm putting this x of n into two pieces. X sub a of n and x sub b of n. X sub a of n is slower or faster than x sub b of n. Thumbs up if you think it's slower, that's on the top, and thumbs down if you think it's faster. Okay? I have two component parts of, and don't answer until I give you the 3, right? So I'm going to count to 3, but now you're comparing these two pieces that make up x of n. X sub a is 1, 2, 3. So faster is down, slower is up. Where is 1/2 relative to 3/4? I would just plug in some n's. I would say, okay, 1/2, 1. 1/2 squared is 1/4. What's 3/4 when you square it? 9/16. How does that compare to 1/4? It's much bigger. What about we cube those two and compare them? Which one's collapsing quicker? The one that's closest to z equals 0. The one that's closest to the origin in the z-plane. This is, in fact, supposed to be x sub a of n is faster. Now, if I said, well, describe x sub b of n, how would you describe that? Slower. But how did we also refer to something that was slower? It dominates, doesn't it? So this x sub b of n is a dominant mode. Is that clear? Now, you can now do this in your sleep, right? You know this is the definition of the z-transform. You can now write down all of these terms. And you can say dot, dot, dot on either side. And looking at this possibility, you know this is zipping off to infinity. That allows you to plug infinity in here to this particular expansion, and that then forces all of those pieces with negative arguments in the sequence to 0. That now says that x sub b of n and x sub a of n are both causal. Since x sub b of n is our dominant, let's focus on that. That's what is going to be seen for the longest. It dominates the response. X sub b is causal, as is x sub a. X sub n is equal to 0 for what values of n? N is less than 0. And what can we say about the region of convergence? Bounded or unbounded? In this possibility, possibility number 1 in that sketch. We allowed z to go off to infinity, didn't we? So this was unbounded. X sub n, was it bounded or unbounded? It was bounded. Since we had these poles inside the unit circle. And if we looked at this particular possibility, the unit circle lies on top of the region of convergence. So we know our sequence that results is going to be bounded. Irregardless of whether it's a causal or non-causal, just this connection of unit circle relative to our region of convergence, we know we have bounded, and now because of this specific point, or this extreme point going off to infinity, we know we're causal. So we know that these two are connected. Let's look at possibility number 2. What do we have? We had poles at 1/2 and 3/4. We said we weren't going to change those. The next possibility, let's just make it, and I know you're already complaining at my non-symmetric drawing, but you can make yours much better. Now our region of convergence is a disk. And what can we say about the region of convergence relative to the poles? In this case, our region of convergence is interior to all poles. And what's a convenient extreme value in this region of convergence? That's the origin, or 0. So this z equal to 0 belongs to the region of convergence. And do you now see how you can use that in this possibility number 2, this expansion? Which of these pieces have to vanish, or coefficients? Which sequence terms have to disappear, or have to be 0? Now if we let z go to 0 and we're dividing by 0, those terms would blow up unless we have these pieces actually equal to 0, and all of those. So that now we know that our sequence in the time domain is defined for negative arguments, or it's now anti-causal. The structure of our response is exactly the same. Coefficient scaling one of the modes to the n, plus another coefficient, a different coefficient, times 3/4 to the n. But what do we know now? We now know when this is defined. We know the values of n when this is true. It's when it's anti-causal, or when n is less than 0. What's another way that we could write this? With a switch. What's in my argument of the unit step? I want to turn this on when my switch has a non-negative argument. It's minus n minus 1. Now when n is equal to 0, that argument is negative, so my switch is off. But when n is minus 1 and less, it's positive argument, the switch is on. X sub 2 of n, how does this behave now in terms of its bounded or unbounded nature? I now have 1/2 to the minus 1, 1/2 to the minus 2. Now that 1/2, you could sort of just put it on its head and say that's 2 to the 1, 2 squared, 2 cubed, because n is negative. That's going unbounded. X sub 2 of n is unbounded. And in this picture, is the unit circle contained in the region of convergence? No. Duh. If it is, it's bounded. If it's not, it's unbounded as far as our sequence is concerned. So you draw some of these things on your paper, you can say quite a bit about the behavior of what's going on. And we're trying to what? Make sure that we understand the connection between region of convergence and the z-transform and its time sequence behavior. Yes?
So can a time sequence and a region of convergence both be bounded or unbounded, or they have to be
So now the question was, do we have to have one or the other or both, or what's possible? Can we have a bounded region of convergence and a bounded sequence in time? Can you draw that? Now. Don't do that. Don't give up. Sketch that. What could you say? You could say, well, the question was, where am I? Possibility 2. Let's do this, except now, why did this misbehave? Because my poles were less than 1. What if I had something, I want to add a page. Can I do that? Boy, it just magically appeared, and luckily I didn't show you the exam. Suppose now you had this, 2, and now your region of convergence is here. Is the region of convergence bounded? The ROC? What time of what range of n is this time sequence true for? What is little x? I'm going to call this little x sub 4 because 3 is yet to be worked through in the remaining time that we have. What values of n is this, and what is the structure? This is alpha 4, 2 to the n. Yes? What values of n is this true for? This is anti-causal. Is that sequence in the time domain bounded? Sequence in the time domain bounded. Region of convergence bounded. We can have both, can't we? So they don't have to be opposite. Did that answer your question? Now I have to somehow get back to the right spot without showing you the exam. And I should reward your patience or your tolerance of me. But here, possibility number 3. You only have to tolerate it for just a short amount of time. Where were these? 1/2 and 3/4. What have we not done? It's almost dinner time. I know it's not quite donuts, but maybe bagel. We could have an annular region. Our region of convergence now, okay, humor me, make sure that you draw yours better, but do you see that the region of convergence doesn't contain any pole, and it's between those. So now the region of convergence is that region of convergence bounded? What can you tell me about the structure? Isn't it this? It's exactly the same, but now what do we have to do with, are these both true for the same index ranges? Is 1/2 raised to the same ends as 3/4? Where is 1/2 relative to our region of convergence? I know that's kind of putting the pressure on, but where's the region of convergence relative to 1/2? It's outside. What did we say that meant with respect to those poles? When were they on? Causal. So now could we do this? Could we say, let's turn that one on there. Switch it on. 3/4 is exterior to the region of convergence. So what does that make it? That's anti-causal, so we can turn it on. And now in one line, we've drawn our x sub 3 of n, our time domain sequence. Or we could do it this way. We could do it as this is n greater than or equal to 0, and this is n less than 0. Can you tell me anything about, so this was what? The pole was interior to region of convergence, or you could say the region of convergence was exterior to that pole, however you want to say it. But now to be consistent, let's say this pole is exterior to the region of convergence, or the region of convergence is interior to that pole. That allows us to say which one's causal, which one's anti-causal. Are they both bounded? 1/2 is raised to n, where n is positive. That's 1/2, 1/2 squared, 1/2 cubed. That looks good. What about 3/4? 3/4 to the minus 1, 3/4 to the minus 2, 3/4 to the minus 3. That's going unbounded, isn't it? Because it's really 4/3 to the first, 4/3 squared, 4/3 cubed. It's going unbounded. This bad boy is unbounded, and that destroys everything. What can we say about the unit circle relative to the region of convergence? Is the unit circle in or contained or lying on top of the region of convergence? No. So what could you immediately conclude? Without really knowing which one's which, you could now say something's going unbounded. Maybe not everything, but something has to be, because my region of convergence does not contain the unit circle. We getting more comfortable with this connection between frequency domain, transform expression, time domain expression. When can we make the unique connection? You have to be given a region of convergence, don't you? Once you have transform and region of convergence, you can invert. You can go back into the time domain. Given a sequence, which you will be given on Wednesday in the exam, given a sequence, you better be able to find the Z transform and when, or the pattern for your region of convergence. We'll pick up with this material, Unit 3 material, after exam number 1. Good luck.